to stare down Python's surprising internals. Please make him welcome.
Chris. Oh my goodness, thank you all so much for coming. This is especially exciting for me because for the last 5 or 6 years, I've been working behind the scenes, helping run the green room and make sure that speakers get to their tracks on time and they have everything that they need. And this is going to be my first time up on stage actually giving a talk. So I'm really excited you could all come. Pursuant to that, if you wouldn't mind taking some great photos of me and tweeting them at me, I would really appreciate that. My Twitter's just up there. So, overall, Python's a pretty great language. It's got, a few decent packages, a pretty fantastic community, and overall, it's not very surprising. But only overall. Every now and then, you run into some weird little problem. Something that you can't explain, something that your coworkers can't explain, and sometimes that really smart friend of yours from that meetup, even they can't explain. And this is where the rubber really hits the road. This is when you draw on all those years of experience you have as a programmer, those thousands of dollars you put into school, and prove to yourself and to the world that you are, in fact, a real programmer. But I'm here to tell you that there is another way. It might not be a better way, or even necessarily a very good way, but it's definitely an interesting way. So over this talk, I'm going to be telling you the story of answering a Stack Overflow question about some strange performance characteristics. And I'm going to be doing that working mostly from first principles. I'm going to show you how to use dis.disassemble to read Python bytecode, talk a little bit about the Python virtual machine, and then dive into Python's C implementation. By the time we're done, I hope that you're going to have some new trivia you can use to impress friends at parties, and also some practical tools you can use in your day-to-day development. Now, I'm going to be using Python 2.7 for this talk. I've gone through most of the examples in Python 3.6. They should mostly work. And when there are differences, like for instance dis.dis instead of dis.disassemble, I'm going to do my best to point those out. So here's the Stack Overflow question that caught my eye. If you can see, oh, we can't really read that. So the question is, why is string x in tuple of string x faster than x string x equals string x? And that seems really strange at first. I mean, come on, equality is about the simplest thing you can do, where with tuple membership, we have to create a tuple, we have to go test for membership, and then at some point we also have to test for equality. One should be a strict kind of superset of the other. So of course, being a good empiricist, the first thing that I did was pull out IPython and verify that I could reproduce the result for myself. Now, just as an aside, we're going to be having a few asides here because I like asides. If you haven't used IPython's %timeItMagic, it's incredibly useful. It will automatically figure out how many iterations of the loop it should run to give you a reasonable result in also a reasonable amount of time, so that you aren't waiting 2 years for 1 million iterations of opening a file to finish. Anyway, getting back to our problem. We found that we can reproduce the result, but that raises the question. If we're not going to be Googling this, what do? Where do we start? The first thing that we do when we're digging into what Python's doing under the hood, at least at the Python interpreter level, is we use dis.disassemble. Dis.disassemble lets you take disassemble Python code and see the underlying bytecode. Now, you've probably heard Python talked about as an interpreted language in contrast with compiled languages like C++ or Java. But that isn't actually strictly true. Python does have a compiler that runs automatically over every .py file when it's first imported or first executed. Those are the .pyc files you see littering your system. That compiler takes the Python bytecode, the stuff that you write, and compiles it down to bytecode. Dis.disassemble is the module that's going to let us take that Python bytecode and see the specific Python virtual machine instructions that are being executed. So here's a simple example. There's a lot going on, so we're going to walk through it one step at a time. The first 3 lines you're probably already seen before. We're importing a module, defining a variable, defining a function. The next line is where things start to get a bit interesting. This is the call to dis.disassemble. And specifically, we have the function and the func under code attribute. Now, I should note in Python 3, it's actually dundercode. But to understand what's going on here, we need to dig into functions just a little bit more. So, just like everything else in Python, functions are objects with a bunch of attributes, and we can use the dir built-in to list those attributes. There's a whole bunch of really, really fascinating stuff in there, and I'm going to be saying this a bunch during this talk. After this talk, you should really pull out an interpreter yourself and dig in and start seeing what's there. At the moment, though, we're just going to be focusing on one attribute, func under code, or in Python 3, dundercode. Func under code is the object that describes the actual code associated with the function. And it's got some interesting information. It's got the function name, the file that the function was defined in, and even the line number. And again, even within func code, there's a whole bunch of really cool stuff, and you can do some probably pretty disgusting tricks there. I don't see Dave Beasley anywhere, so we should be safe. But for the moment, we're going to be focusing on the CO under code attribute, and this one is actually the same in Python 3. CO under code is a string, byte string, that contains the exact same compiled bytecode for that function that would appear in a .pyc file. This is the full implementation of the function, and we can see that if we use dis to disassemble it. Now, notice that this is just about the same disassembly as before. We're missing a bit of metadata like line numbers and variable names, but the instructions are the same. Now, for the more observant among you, though, you're going to notice that the hello format string doesn't appear anywhere in that bytecode. Your first take-home assignment is to figure out where is that hello format string stored. Anyway, we're doing okay for time, so I'm going to do one more little digression into function objects, and that's the func closure attribute. So if you haven't heard the word before, closure is a fancy computer science term for a function that stores references to variables that aren't inside the function itself. So for example, this hello closure inner function that's defined inside the outer hello closure function makes reference to this message variable. That message variable, though, isn't defined in the function itself. It's defined outside the function. So that when the hello closure inner function is returned, but when the hello closure inner function is returned, it still somehow has access to that variable. Now, if you're used to Python, this might not seem like a surprising thing, but if you've come from other languages, like for instance C or older versions of Java, this is actually quite a novel concept. So how does that work? Well, that's the func under closure attribute. Func under closure contains a tuple of all of the different variables that are being closed over. And now for the pedants in the room, it's actually not the variables, it's actually these objects called cells that reference the variables, which mean that the outer function can change their value without having to go and monkey with the tuple of all the inner functions and But the important point is that each function actually stores along with it a reference to all the variables that it's closed over. And one of the kind of neat consequences of that is that it's actually possible to, at least in theory, to build a serializer that will be able to take one of these closures, serialize it, send it across the wire, load it up, and evaluate it on another computer exactly like it was. Now, this is a bad idea, and I really hope none of you do it. And if you do, don't do it, but definitely don't put it up on PyPy, and definitely don't tweet about it. Anyway, your little bit of homework from here is to figure out why, even though there are actually two variables in scope at the time that hello closure inner was defined, its func under closure attribute, its func under closure tuple, only has one element in it. What happened to that other variable? I don't know. You'll have to figure it out. Anyway, that was a nifty little digression, but getting back on track. So now we know kind of what it means to disassemble the function code. So let's start looking at the output of the disassembly. Now, even if you've never seen disassembled Python or disassembled anything before, you should be able to make some reasonably educated guesses about what's going on here. So first, loading the string, the format string. Second, we're loading the value of a variable. We're building a tuple. We're applying the binary modulo operator, and hopefully you can see that. Well, that's okay. We're applying that binary modulo operator. Now, if you recall, the modulo operator is normally used for getting the remainder of divisions, but Python overloads it to also do string formatting, which some people don't love, but I'm going on record as saying I absolutely love. And finally, we're storing the result of that format back into the message variable. Next line, we're loading the value of that message variable. We're printing it, and this is, of course, where Python 3 would be a little bit different, because in Python 2, print is its own opcode. In Python 3, it's just a regular function. And then, since the function didn't explicitly define a return variable, we're returning none. So, to go into just a little bit more detail on what's going on here. You've probably noticed with each of those machine instructions, they're a simple instruction that just takes one argument. So for instance, the binary modulo, it's one instruction with one argument, modulo. Even though an actual, logically a modulus takes two arguments, the left side and the right side. So that's because the Python interpreter, it's also called a virtual machine, is a particular kind of virtual machine called a stack machine. And in stack machines, in general, instructions operate on values and pass values around by pushing them onto and popping them off from a stack. Now, this is in contrast with a register machine, like an Intel or an ARM or whatever, that's in your laptop or in your phone, and they have a whole wide variety of operators that can take all sorts of functions or all sorts of arguments, and they can access memory and registers and all these different things directly. So to explain what I mean, I'm going to use the example of this simple math equation, 1 + 2 × 3. In our little fictitious stack machine here, the instructions that we would use load 1. Now that's going to put a 1 onto the stack, we'd load 2 onto the stack, and 3 onto the stack. So now we have our stack is kind of a list of 3 items. And when the multiply instruction comes around, it's going to pop those first 2 items off the stack, the 2 and the 3, multiply them together, get 6, and put that back on top of the stack. Next, when the add comes along, add is going to take the next 2 items off the top of the stack, the 1 and the 6, add them together, and put the result back on the stack. Stack machines are cool, and they're used a lot because they're ridiculously simple. Like I just explained most of the things you need to know about them right here. They're really easy to implement, they're really easy to reason about, and importantly these days, they're also really easy to optimize. So in fact, in addition to Python, Java, PostScript, the cryptocurrency Ethereum, and Rubinius, which is a Ruby interpreter, are also implemented with stack machines. Whew. Okay, so that was a lot. Time to get back to the problem we have at hand here. So if you remember, we're trying to figure out why this tuple membership is slightly faster than the equality. And the first thing we're going to do is we're going to use dis to disassemble 2 functions that both perform equality and membership, and see what instructions are being executed. So first, the instructions for membership. Second, for equality. And just by the way, if you're wondering, these numbers here are indexes into the function co under constants tuple that you may remember from previous slides. And when we compare the two side by side, we can see that they are virtually identical. The only 2 little differences here, the one is obviously we're using a tuple in the second instead of a string, and the second is that compare operation, number 6, which is in the first version equality, and in the second version, in membership. Now, to go any deeper, this is as deep as the Python interpreter itself can go. To start seeing what's happening next, we need to dive under the hood into Python itself. So again, I'm going to be using Python 2.7 because that's what I'm a little bit more familiar with. I've gone through all this in Python 3.6, and it seems to be virtually identical if you're playing along at home. Yeah, so we're going to start. We're going to grab a tarball, extract it, and just do a simple search for compare op. Now, when you do the search, you're going to get a bunch of different hits, and I'm going to, in the interest of time, narrow them down to two that I want to point out. The first one is peephole.c. Peephole.c it's really, really interesting. It performs these in-place micro-optimizations on the Python bytecode. For instance, it'll transform the statement not A in B into the statement A not in B. Because not A and B is actually two instructions. It's a membership and then a negation, where A not in B is actually just one instruction, a negated membership. I obviously don't have time. I wish I had time and understanding to go through and explain it all, but Alison Kapoor has a really, really good blog post on this. If you Google Python peephole.c, you'll find it, and she goes into a lot of detail there. In this case, though, the one that we're going to be interested in is ceval.c. And again, before we dive into that, just a quick refresher. These are the two sets of instructions that we're comparing, and specifically what we're going to be trying to figure out is what happens at that line 6, the compare op, and why these two are different. So now is when we pray to the gods of demos. Oh ho, look at that. Can I get thumbs up when this is big enough? Ah, beautiful. Good. So here's where we're going to be starting our journey. This is ceval.c, which is the main evaluation loop in Python. So if you go back, if you think back to that bytecode, the bytecode is just like a string of instructions. And ceval.c just has a massive loop, which is read one instruction, execute that instruction, go on to the next instruction, and we just keep doing that forever. If you're a little bit familiar with C, you'll know what a switch statement is, and the point in the code that we're at right now is the massive switch statement, which is branching on the instruction being performed. And in particular, we're at the line that performs the compare operation. Now, the reason you don't see the keyword case there is because the target macro expands to some nifty tricks that let the computed goto optimizations that were put in place a few years back work. Again, really super cool. Google computed goto Python, and you'll get. It's really neat how that works. But anyway, if you're not that familiar with C, all that you need to know is this is the bit of code that gets executed when we're performing a comparison in Python. The first thing you're going to see here, the pop and top. So remember, we're on a stack, so pop takes the top item from the stack. That's, in this case, going to be one of the strings, and top just peeks at it to grab it out. Reading through, without knowing anything more about what's going on in Python, we can guess kind of based on the context here that this pyint check exact is, I'm checking to see if this is exactly an integer. Which leads me to one of the things that I really love about digging through the Python, or really any project source code, is you get to learn all these neat little tricks that the maintainers put in, and then if you get really ambitious, you can go through and git blame and find the exact commit and read all the messages around it. And in this case, what we're seeing is that there's an optimization in place so that if you're comparing two integers, instead of going through all the complex logic that we're going to be seeing in a minute, we're actually just shortcutting and doing the comparison right there in line so that can be much faster. Scrolling down, though, we're going to get to this line here. This is the actual starting point of the comparison. Recall that oparg is either going to be an equality or a membership, and oparg stands for opcode argument. V is going to be the right-hand side of that comparison, so the string or the tuple, and W is going to be the string X. We're going to pick arbitrarily to follow the equality case first and trace through to see what happens. So we've got this switch statement here. Switch, if you don't know C, is kind of like a set of chained if-elses, and it's going to say, you know, if the operation is not comp in. We're going to scroll down. We don't see an explicit PyComp under EQ, which again is the equality operation, which if you were doing this on your own, you would probably spend 5 minutes searching around the source code until you figured that one out. And find that the PyComp EQ is handled here. Now, one of the things you're going to see me doing as I'm flying through this code is jumping to definitions. So I'm using Vim, and in Vim, I use control and then close square brace to do that. If you use Sublime, they have the go-to symbol in project with Command-Shift-R, and I'm sure any other editor you're using will have similar functionality. And now, if the only thing you take away from this talk is how to do that, it's been way worth your time. But hopefully you'll get one or two more things. So diving into rich compare, we can see, we're just going to read through, make sure we're not doing too much recursion here. And the first thing we get to is this if statement. And we're going to go right to left here. So the PyInstance check. So what's a PyInstance check? Now, it's used to distinguish between old-style classes and new-style classes. If you're in Happy Land of Python 3, you can close your ears for a little while because this isn't relevant to you. But if you're like me and you're on Python 2.7, you'll know that old-style classes are what happens when you forget the object in a class definition. And they were introduced, new-style classes with the object were introduced in 2.1, when there was a bunch of updates to the object model that would be backwards incompatible. So if you like what we're doing here and you want to kind of try something on your own, I'd recommend trying to figure out exactly why the @property decorator doesn't work in old style classes. But anyway, we'll suffice it to say that PyInstance check will return true because these classes are strings. And then going to the left-hand side here, we see the test to check whether the object's types are identical. Now in C, the left-hand sides are things called structures. They're, for the purposes of this demonstration, equivalent to objects, but they really aren't, and I'm going to get lots of hate mail if I imply that they are. So we know they're two strings. They're the same, moving down. The next thing we see here is this rich comparison. So what is a rich comparison? Well, again, pre-Python 2.1, you could only really define one comparison method that would return -1, 0, or 1 for two objects. The new style classes in Python 2.1 let you define all these rich comparisons like dunder EQ, dunder GT, dunder LGT, whatever. And TP rich compare is the function at the C level that handles all that. It's a little bit easy to miss. It took me a couple times the first time I was reading. But this is the line that we're actually interested in. This frich is the rich compare operation for the objects we're comparing. In this case, they're strings. Their type, again, you would figure this out if you were doing it on your own, but I'm going to tell you for sake of brevity, is PyType string. And we're going to be looking for the rich compare function. So I'm going to jump to that definition. At the C level, you'll notice that instead of defining objects with like helpful keywords and whatnot, we just have a big list of functions, and somebody has had to go through and make sure they line up all these comments on the left-hand side. These comments, these functions, if you notice them, you'll see that they're actually the same things as the dunder magic methods for the most part that you're used to in Python. So for instance, TP-repr is the same as dunder-repr. In this case, though, we're looking for rich compare. And there it is. So this is the function that you're going to get when you compare two strings. Anytime two strings are compared in Python 2.7, this is your function. Now, before we read any further, one of the things that I want to point out and remind you of is when we were looking at the disassembly, the two load const opcodes had the same argument. That meant they were actually loading exactly the same string. And this is happening because when Python loads a module, it actually goes through and deduplicates some of the strings. Now, this is some of them. There's lots of magic logic around that, and that logic is fascinating. And I would really encourage you to go check it out afterwards. But for the moment, we're only going to be concerned with the strings that it is interning. And to show you an example of that interning, interning is the process of deduplication. You can see that if I have two variables that reference the same string, they point to the same memory. They're identical values. And this is possible in Python because in Python strings are immutable. But you'll notice that often languages like Ruby that have mutable strings often have a symbol type, which is kind of like an immutable string. So we go down, we notice those two are identical, and this is where we end this portion of the journey. We're seeing we get the PyTrue return. And, well, that's what happens when we compare two strings. So we're going to pop back up here and now go through that same journey again, but comparing the membership. So PyComp outcome, we know that op this time is going to be PyComp in, and it's explicitly called out here. It uses PySequence contains, which, again, we're going to goes through similarly to equality. There, we're checking the type to see if it supports this, sequence membership. The PyTuple type does, and the chain of attributes we're looking for is here. So TP as sequence, and look at that, tuple contains. So this is another thing that I love when I'm reading through like Python source code, is it looks all big and fancy and like abstract, but then you get like to the, the rubber hits the road, and this is where we're just doing a computer science 101 type for loop over the elements in a tuple. The big difference though here is we see this PyObject-rich compare, but this time we're calling PyObject-rich compare bool, which is a slightly different function. And the very first thing that it does here is that identity check. And if you remember that interning, well, interning works the same for strings in tuples as outside of tuples, which means it returns immediately here. And there's the story of what happens with the identity compare, or with membership. Now, if we were doing this properly, we would go through and we'd see, kind of trace it in a high level of detail, what instructions are being executed, but I'm short on time and I've done this for you, so I can tell you that these are the two sets of instructions that are executed when on the left-hand side we have the membership, on the right-hand side we have equality. And you can see that the one is significantly longer than the other, and lo and behold, it's also slower than the other. And now I realize that was somewhat anticlimactic, but you're programmers and you're used to computers being pretty dreary. So hopefully though, and I need my notes here for this, so I'm just going to go from here, you'll know that, that Python isn't magic. You can see that even though sometimes it does these kind of magic looking things, it's always possible to peek under the hood and see what's going on. And while this might not be a problem you'll ever have, hopefully you can see how you could take those same sorts of techniques and apply them to problems you will have, like your Django model not saving, or your lib3 not pooling connections properly. Oh, and finally, you remember this code from the beginning? Now you should be able to explain why it works, because the tuple membership is shortcutting to identity. Now, quickly in the last 2 minutes before Chris kicks me off stage, there's three things. One is a piece of homework. So you know how you can override methods on an object, but you can't override dunder-len. Figure out why that is. Second thing, I'm hiring. Yeah, my company is called Akindi. We make Scantron-style bubble sheets that are a little bit less terrible. Teachers can print them from any printer, scan them from any scanner, get all the results online. If you're in Toronto or thinking about moving there and making teachers' lives less terrible sounds interesting, come talk to me. Finally, I'm super into knots, and I'm going to be having a knot boff at 2 o'clock in B2. 112. So if you're, I'm going to be geeking out about knots. I'm going to be showing you some of my favorites and hopefully learning some new ones. So come on out to that. It'll be a great time. Thank you.
We have 10 minutes until the next talk, and it looks like, can we please stop people from walking in? We have a full house who need to get out of here at the moment. There's a big crowd outside, so if you need to leave, please make sure you leave quickly.
And when there are differences, like for instance dis.dis instead of dis.disassemble, I'm going to do my best to point those out. So here's the Stack Overflow question that caught my eye. If you can see, oh, we can't really read that. So the question is, why is string x in tuple of string x faster than x string x equals string x? And that seems really strange at first. I mean, come on, equality is about the simplest thing you can do, where with tuple membership, we have to create a tuple, we have to go test for membership, and then at some point we also have to test for equality. One should be a strict kind of superset of the other. So of course, being a good empiricist, the first thing that I did was pull out IPython and verify that I could reproduce the result for myself. Now, just as an aside, we're going to be having a few asides here because I like asides. If you haven't used IPython's %TimeItMagic, it's I'm here to tell you that there is another way. It might not be a better way or even necessarily a very good way, but it's definitely an interesting way. So over this talk, I'm going to be telling you the story of answering a Stack Overflow question about some strange performance characteristics. And I'm going to be doing that working mostly from first principles. I'm going to show you how to use dis.disassemble to read Python bytecode, talk a little bit about the Python virtual machine, and then dive into Python's C implementation. By the time we're done, I hope that you're going to have some new trivia you can use to impress friends at parties, and also some practical tools you can use in your day-to-day development. Now, I'm going to be using Python 2.7 for this talk. I've gone through most of the examples in Python 3.6. They should mostly work. Incredibly useful. It will automatically figure out how many iterations of the loop it should run to give you a reasonable result in also a reasonable amount of time, so that you aren't waiting 2 years for a million iterations of opening a file to finish. Anyway, getting back to our problem. We found that we can reproduce the result, but that raises the question. If we're not going to be Googling this, what do we do? Where do we start? The first thing that we do when we're digging into what Python's doing under the hood, at least at the Python interpreter level, is we use dis.disassemble. Dis.disassemble lets you take disassemble Python code and see the underlying bytecode. Now, you've probably heard Python talked about as an interpreted language in contrast with compiled languages like C++. Overall, it's not very surprising, but only overall. Every now and then, you run into some weird little problem, something that you can't explain, something that your coworkers can't explain, and sometimes that really smart friend of yours from that meetup, even they can't explain. And you know, this is where the rubber really hits the road. This is when you draw on all those years of experience you have as a programmer, those thousands of dollars you put into school, and prove to yourself and to the world that you are, in fact, a real programmer. But
to stare down Python's surprising internals. Please make him welcome.
Chris. Oh my goodness, thank you all so much for coming. This is especially exciting for me because for the last 5 or 6 years, I've been working behind the scenes, helping run the green room and make sure that speakers get to their tracks on time and they have everything that they need. And this is going to be my first time up on stage actually giving a talk. So I'm really excited you could all come. Pursuant to that, if you wouldn't mind taking some great photos of me and tweeting them at me, I would really appreciate that. My Twitter's just up there. So overall, Python's a pretty great language. It's got, a few decent packages, a pretty fantastic community, and